So welcome. This is your community observatory. I see a lot of familiar faces, so I don't need to do much here other than we've been at this for almost 17 and a half years. It's all done by volunteers. And we had a lot of fun in the middle of February imaging the space Tesla as it went flying out towards Mars. We were successful in capturing it when it was over 3 million kilometers distant. And 2 different times we held the world record for the distance imaged, and we submitted them to the Minor Planet Center and to the Space Weather and got lots of kudos. And Robert Miller wrote a nice article about us in the News Times, which nobody reads. But it was neat. And my wife and I were at the launch of the Falcon Heavy in Florida, and I got a couple minutes of imaging of this thing. It was just so cool to do. We imaged it till it was about 50 kilometers up and going 5,000 kilometers an hour downrange. And my little handheld camera was still finding it, so it was really cool. Then we came back. In our last image, we imaged it at a distance where its size would be equivalent to us imaging a matchbox car at the distance of Tel Aviv from this telescope. So we were impressed. This stuff's better than we thought. So that's pretty good. So I use that to point out that it's serious equipment. This can do serious science. So this is an update on exoplanet discovery, successes and future plans. And there have been many successes. This is a hot part of astronomy. And so we're going to feature the amazing discovery of the Trappist-1 solar system, which is 7 planets, and 3 of them are in a habitable zone. This poster here is one that represents this Trappist accomplishment, and we'll talk about it a little because it's actually it's not a photograph, but it's actually actual locations of things. So it's when I first saw it, I didn't understand that. We'll look at that for a minute. So we're going to explore at the end what's ahead. There's one of my typos. Is ahead. That's really far out. So finding exoplanet systems in huge numbers, determining ever greater detail about them, directly imaging them, gaining serious knowledge of their atmospheres, finding ways to discover life forms. These are all on the agenda, and there's money being invested in every one of these facets of exoplanet research. And I knew very little about most of what's coming until I started studying a couple weeks ago. So it's been a 20-year journey searching for planets and now finding ways to search for life. It took nearly 20 years from 1995 to confirm the first 1,000 exoplanets, and that we made headlines at first. Then they started announcing them in batches, and people started yawning, but it's very demanding work, and it's really catching fire. The Kepler Space Telescope changed the game when it went up in doing repetitive searching of a region of space that happened to be in Cygnus and yielded about 2,650 planets in 2 mission phases. So that proved that they're everywhere, because it wasn't a huge part of space. And if you find that many in that little area, you can do some extrapolation and get big numbers. So 30 or so confirmed exoplanets that are less than twice Earth size in the habitable zone, and we'll talk about habitable zones. So this is where we are today. This was from the Scientific American of this month, which I trust. 3,567 exoplanets discovered. That's a lot. But you ain't seen nothing yet, as they say. So the discovery type, primarily because it's so simple, is the transit method, meaning that we're imaging the diminution of light from a star when a planet eclipses it goes in our line of sight. So not a huge percentage of them do that, but there's enough that do that we can really make hay with that technology. So the Kepler, all of the Kepler work has been done with transit method. Without Kepler, there are other telescopes, ground-based telescopes, even some amateurs with big telescopes have found transiting planets. Then Doppler basically means that there's redshift and blue shift of light from stars based on fairly large planets changing the location of the star itself ever so slightly. And so that's yields less and is not as much used, but it is in fact one of the toolkit techniques. And the planet types based on planet radius, giant ones that are close to the stars are the easiest to get, obviously. So we get a lot more of those than others. Super Jupiters, big things that are halfway between Jupiter and a star. Then sub-Neptune, which means Neptune is the smallest of the gas giants, so things between Earth and Neptune. And then super Earths, which is like up to 4 or so Earth radiuses, and then Earth size, not so many. Orbital periods, long orbital periods are tough because the transits don't occur very often, so you can't really get any patterns. So you notice out here, 5 to 50 days, that's the sweet spot. So sub-Neptune, 5 to 50 days, we found a whole bunch. And we're trying to expand to be able to do more sizes and more distances. So somehow the international astronomy community kept secret an amazing set of discoveries for well over a year, almost a year and a half, called the Trappist-1 solar system. It was one of the greatest discoveries in this whole field of exoplanet searches. They found, and we'll walk you through how this happened, a 7-planet solar system of Earth-sized planets. So it wasn't too many years ago we hadn't found any Earth-sized planets. They found a solar system that only had Earth-sized planets, 7 of them. Wow! So they were pretty excited about this. So they waited and had a giant publicity announcement and all kinds of seminars, etc. 3 of them in the habitable zone. We'll get to that. The first 2 were discovered by a 20-inch telescope. This is not, the Hubble or some giant thing. It was a little telescope on a mountain in Chile. The next 5, a combination of the very large telescope that's in the same location as the 20-inch, and the Spitzer infrared telescope. It's a NASA telescope. And they ganged up on this solar system. So many telescopes that participated since, the Hubble, the Keck, you name it, everybody wanted a piece of the action. So, and they've all contributed, which is kind of fun to know that we could have that kind of cooperation in this world. So the study's ongoing, and it opens the door to more such discoveries. There may be, very likely, many such systems around small red dwarf stars. Yes, sir. Kevin.
My name's Walker.
You're Walker, right? I'm sorry.
Sorry.
I get people confused.
Sorry.
Hi, Walker.
Do you see that poster that's being projected onto the screen?
Do I see it?
I mean,
Like this poster, you mean?
Yeah, that one.
Yeah, we're going to talk about that.
Yeah. Does that?
I will tell you about it.
Sorry.
It's one of the most exciting parts of this. Walker's always a step ahead of me. So we have a couple of little video clips. One's from the European Space Agency and one's from NASA.
I think it's at the end of the video.
Oh, thank you. Is that better?
Astronomers have discovered 7 Earth-sized planets orbiting a tiny nearby star. At least 3 of the planets could harbour oceans of water, making them possible homes for life.
Listen carefully now. Is it loud enough? Can you hear the back?
Yep, I can hear it.
Just 40 light-years from Earth lies Trappist-1. It's a small, dim red star known as an ultra-cool dwarf. only slightly bigger than Jupiter. In early 2016, astronomers using the small robotic Trappist Telescope found the first planets orbiting the star. With follow-up observations, a total of 7 worlds have now been identified in the system. Astronomers discovered and learned about the planets orbiting Trappist-1 by studying tiny regular dips in the star's brightness. These are caused by the planets passing in front of it and blocking some of its light. Observations were made using telescopes around the world and in space, including ESO's Very Large Telescope in Chile and NASA's Spitzer Space Telescope. The results? The discovery of an amazing rich planetary system with 7 planets, having similar sizes and temperatures to the Earth.
This is an animation, this isn't real video, but it's accurate.
Although the planet's orbits are very close to their parent star, its low energy output means that the illumination levels they receive are similar to Venus, Earth, and Mars. Climate models suggest the innermost 3 would be too hot for liquid water to exist on anything more than a small fraction of their surfaces. And the most distant and coolest planet is expected to be an icy world. However, 3 planets in the system, Trappist-1e, F and G, represent the holy grail for planet-hunting astronomers, as they orbit in the star's habitable zone. Excitingly, this could mean they harbour oceans of water on their surfaces. This new discovery makes the system a top target for future investigation. With the next generation of telescopes, such as ESO's European Extremely Large Telescope and the NASA ESA James Webb Space Telescope, astronomers could observe signs of water in the atmospheres of these planets. The presence of life also leaves unique chemical signals in a planet's atmosphere, which could possibly be detected on these nearby worlds. Dwarf stars like Trappist-1 are very common in our galaxy, with most expected to host Earth-sized planets. The search for life may find success in a system just like this one.
I'm going to show. So that was the European Space Agency from the European Southern Observatory. Now we're going to give equal time to NASA. Some of it's overlap, some of it's different information.
Imagine a place with not 1, not 2, but 7 Earth-sized planets all orbiting a single star. It's not just science fiction, thanks to a new discovery by NASA's Spitzer Space Telescope. Trappist-1, an ultra-cool dwarf star just under 40 light-years away, plays host to this incredible collection of planets. In 2016, astronomers using the Trappist Telescope at the Observatory in Chile first identified 3 Earth-sized planets here. The discovery warranted extensive follow-up by Spitzer, whose infrared detectors are particularly sensitive to the cool glow of this tiny star. Spitzer devoted over 21 days of nearly continuous observations to Trappist-1, pausing only to send data back to Earth. It was looking for tiny dips in the star's brightness when the circling planets pass in front of the star or transit.
So these vertical bars, as they descend, they are the things that tell the information about the transit.
Data set, astronomers confirmed 2 of the 3 previously reported planets and found the third was really 3 different ones. Plus it discovered 2 more, for a total of 7. The transits tell us a lot about these planets, including their size, orbital period, distance from the star, and for some of them, their approximate mass and density. NASA's Hubble Space Telescope followed up by studying the transits to look for the chemical fingerprint of hydrogen gas in the exoplanet atmospheres. While its search continues, none has been found yet, adding support to the idea these are all rocky terrestrial worlds. That makes this a planetary system that is both familiar yet exotic. It is likely most, if not all, of these planets perpetually keep one face pointed toward their star, a phenomenon called tidal locking. This would create large temperature gradients across their surfaces and offer the possibility that liquid water could exist on any of them under the right conditions. Moreover, if you could stand on the surface of one of these worlds and look up at your neighboring planets in the sky, they would at times appear larger than our moon looks to us. That's because Trappist-1 is only a little bigger than Jupiter, and the Trappist-1 planets orbit only a little farther apart than Jupiter's moons. Interplanetary trips here would be measured in days, not months or years like in our solar system. For now, we can only speculate what these exoplanets might be like, as we still know relatively little about them. Upcoming missions like the James Webb Space Telescope will study the Trappist-1 system in greater detail and uncover more clues about the atmospheres and compositions of these 7 Earth-sized worlds.
Really get that one over.
So, this September 17th, 2015, it was the first recorded transit of Trappist-1c. And they didn't know that there was anything other than that. Now, you saw that 20-inch telescope, that's the Trappist Telescope. And people say, why Trappist? Well, the European team that ran it and runs it today is a Belgian team, and the principal investigator's favorite beer is Trappist beer. So a lot of our volunteers can relate to that as a really good basis for a name. So that's the hidden code of Trappist. So a month later they found a second one, then third one, 3 more in October. Then in December they actually found C, D, and F with a very large telescope. But they didn't know that they'd found all this. They couldn't really decode that. It took them a long time to peel that information out. And it wasn't until early last year that the H planet was found. Now the way they code exoplanets is the star is the base, and the first one discovered then, the first planet, is the B, then the C, then the D. So if you see a D, it's the third discovered planet. It doesn't necessarily mean it's in the sequence out from the star. It just means that's the order in which they were discovered. So that's their coding system. So it took a while, but you know, in the grand scheme of things, that's not much time. And it's pretty impressive. And it's because they ganged up on it. They brought so many telescopes to bear. So here's the deal. Here's our sun. We all know our sun, and it's 860,000 miles in diameter. It gives off a lot of heat, and it's very bright at visible wavelengths. Now, red dwarf stars are a little different. This is an ultra-cool red dwarf star, which is a very, very common type of star. We don't know how common there is because it's hard to find them, especially if they're much distance away. It's 9% as massive as our sun. It's 2,000 times dimmer, and it's much cooler. And it's brightest at infrared wavelengths. And we don't get infrared wavelengths to Earth. Therefore, infrared telescopes are going to be a big deal in this process. So, doesn't mean it didn't have any visible light, because the Trappist telescope wouldn't have found it otherwise, because we really can't see much infrared light on the Earth's surface. So here's this telescope. It's 4 inches larger in diameter than ours, but it's on a mountaintop, so they kind of have an advantage over us. So they discovered the first two just through, that's what they do for a living, is look for exoplanets. And once they found those, the Spitzer Telescope got engaged very, very soon. And the instrument that led the discoveries of the other 5, that and the Very Large Telescope, engaged together and were able to find the other 5. They're very confident there aren't more than 7, but they're not perfectly confident. Very is a clever word. So here's the deal. Habitable zones. Here's the Earth's inner solar system, the rocky planets. And this green band is the habitable zone. And what that means is that water would stay liquid as the planet orbits the star for millions and billions of years. And for life as we know it, that's an important prerequisite. So we have 3 in the habitable zone. 2 of them are barely in it. Earth's pretty well ensconced in it, which we can be happy about. So if you take this little concentric blue circles here, that is, to this scale, the size of the Trappist solar system. So they're pretty close to that star, and they'd have to be in the habitable zone because the star doesn't radiate that much energy. So if we then take this little disk and enlarge it 25 times, we get a habitable zone that puts the 4th, 5th, and 6th of their planets into a habitable zone. One right in the middle, F, and E is, they're all well into a habitable zone. And so those are the ones, of course, we're most interested in, but we're interested in the whole system. So if we look at this kind of same image again, but add in the 4 Galilean moons around Jupiter, this thing is not hugely different in size than Jupiter. So you all know Io, Europa, Ganymede, and Callisto. That is to the same scale. So Callisto's orbit is slightly bigger than the B star, the closest planet to Trappist. This one's most like Earth. And so habitable zone, and now you see, you get it in scale, the context of it. It starts about where Callisto, where the Jupiter inner moons end. So now we put a lot of telescopes to work on it and discovered an incredible amount of information. It's astounding how much information we got. So Earth has a distance from the sun of 1 unit, 93 million miles. Its planet mass, our mass, m Earth, so Earth is a unit of 1. So that's our reference point. So now if we look across, and the radius is 1 radius. Since we live here, we get to do the numbering system, right? So here's its orbital, our orbital periods. You know these pretty well. Theirs are in days, 1.5 days, 6 days, 12 days, and about 20 days. So Mercury is the fastest orbiter at a little under 88 days. The planet radius, look at the planet radiuses. They lay right on Earth's radius. But the masses are quite different. So this is 0.85 masses, this is 1.38, this is 0.62, this is 1.34. So if their radiuses are similar to Earth and their masses are quite different, that tells you, you can then calculate their density. So the densities are different. And so then you have to answer the questions, why are they densities different? So the fact that they were able to do this so quickly is pretty amazing. So to give them more character, we gave them imaginary colors so that people could think about the D, the E star, which is the most like Earth. We can give them some characterization. There's no science in that. There's nothing that says this planet would look this way and that planet would look that way, but it gave them a characterization that helps. So, back to Walker's question.
Yeah, sorry
This,
about that.
it's all right. This, when I first saw this, we got this thing from NASA. They sent it out to us, nicely laminated, and it's, I thought it was just an artist rendition, you know, to give you the notion. Well, I was wrong. They know the orbital paths, the difference in orbital speed, the difference in size to the point where this actually represents a point in time, a precise point in time. If you were on Trappist-E and looking out and seeing this alignment, we like alignments in the sky, right? So these four you see are all, these three are waxing crescents, right? This is a waxing gibbous. These two are full, and we know that the star is somewhere right over here, right? And that is an actual calculated location that they already knew about and had observed. So it's pretty cool.
I thought what it since it says voted best hab zone vacation. So what I thought was I thought this depicted a family looking out the window of a spaceship just as it's arriving and is about to dock at that city in the distance so they can start their vacation.
Yes, and that's a good idea for the future. So when you're my age, you might be able to do that. The problem is this thing's 39 light years away, and we can only go about 40,000 miles an hour. So you have to figure out how to get something that travels way faster than what we can do. So these are imaginary people. It's a real set of planets, but it's imaginary people. And they did the same thing from the Spitzer observations. The same thing. They calculated locations of these 7 planets, and then made an artist rendering. So it's very similar to the last one, but instead of being on the E planet, you're out looking at their solar system, and there's a double transit there. So it's a pretty cool way to start visualizing, which is important. They pay people a lot of money to be visualizers. Now, Walker, get your folks to get you some marbles, and you can make a Trappist-1 model. People of all ages, we allow you to do this. I don't know where you buy marbles anymore, but so my children remember vividly 40 years later when we got a grapefruit, a tennis ball, a golf ball, and did the solar system with a flashlight on our bedroom carpet. So this is a cool way to do this. When you do this, and there's a lot you can do because you know the velocities of these and their orbital distance, and you can actually go through a couple days, you know, in 20 minutes of moving them around at their actual relative speeds. I want to do one. Do we have any marbles? Now, one of the more interesting things, the Very Large Telescope observed on December 11th, 2015, 3 planets transiting at the same time. And so they got this weird diminution curve of light. This is light, this is at 98%, this is at 98.4, etc. They got this weird curve and they had no idea what they were looking at. So they studied it, and it took them a long time to tease this information. So those are 3 of these planets. And here, this is the line that indicates the passage time of each one of them. And you see these 2 are like right on top of each other here. Then they spread out because they're all going at different rates. So the people that figured this out, you know, they get my salute for being good at their job. And so the Hubble got in this. You can't do anything without the Hubble joining in. So they joined in, and they've been studying the atmospheres. And the way you do this is, when the planet's transiting, you point the Hubble at this region, and you use the spectrograph and measure the difference in the gas content here versus here, and subtract out the ones that are the same, and what's left is the atmosphere. This is how they're going to be teasing out atmospheres for quite some time. So the Hubble's good at doing that. The James Webb will do that for a living. So it's pretty neat. So they do know quite a bit about the atmosphere, a couple of these. And this is some of the Hubble results. Forget this, it's too complicated. But over here, these are, this is Trappist-1b, so it's the closest one to the star, right? So it orbits the most often. So you can point the telescope and not waste as much time. It's molecular hydrogen rich. It's cloud free. It's water rich. And I can't read this part. Anyway, the point is they know how to figure this out now, which is huge, huge progress. So, can there be life on the 3 planets in the habitable zone? Yes, but. I have a big but, because you heard him talk about tidally locked. A problem, all 7 planets are very, very likely to be tidally locked. That's 2 varies. If it's 3 varies, it means no chance. But it's 2 varies is like 99%. So it's not yet proven that they're tidally locked. But so our moon is tidally locked to Earth. The Galilean moons of Jupiter, tidally locked to Jupiter. All the other large moons in our solar system are tidally locked to their planet. So it's almost inevitable. And that's their answer. It's almost inevitable, therefore we're declaring them tidally locked. So this means a very hot side and a very cold side. And even though that's a small star, these planets are very close, so they can calculate how hot it would be, and the hot side is very uninhabitable. The cold side, very cold. Maybe not as cold as some of the things in our solar system, but so the only way really to have life as we know it is to have it along the day-night perimeter, where there is something that's more temperate, and the poles, because even though it's tidally locked, it still has poles. It's still rotating, right? You all agree with that? So there could be life forms there, and they weren't always tidally locked. Things become tidally locked, but they're rotating earlier in their lives, and we don't know how old they are. But life forms could have happened, and they could be in craters in places at the poles, like we look at Mars and we look at our moon and know that there's ice deposits and places where you could find water and water ice, and we know that there are kinds of life forms that live in ice. So can there be life? And last year, much study has been done of this system. Researchers have determined that all of the planets are mostly made of rock. And additionally, some have up to 5% of their mass in water, which means there's 250 times more water than on the oceans on Earth. We actually don't have that much water. Europa has 2.5 to 3 times as much water as Earth does. So we're 3/4 covered, but it's not very deep. So there's not really that much water relative to other places. You all agree with that, right? So artists have fun with depicting these kind of things. Some water at that day-night zone. So moving forward, that's TRAPPIST. It's fascinating. There are huge numbers of these red dwarf stars. Hard to find, but they're being found. Likely way more than Sun-like or larger. And we've been reading this since we started this observatory, that red dwarfs are the predominant ones, but there's no way to prove it. Now they're saying estimates that possibly as many as 80% of the stars in the Milky Way are red dwarfs, and they're bright in infrared. Possibly as many. There's a lot of hedging in that, but it's big numbers, and in my lifetime we will even begin to be able to count them. So they're possibly the best candidates for finding Earth-like planets in habitable zones are around red dwarfs. Now, if you only have found one, it's hard to leap into these kind of things, but it's been a theory for a while. So the James Webb's coming. Keeps getting deferred. It's going to be sometime next year, most likely, but they've had some technical problems. What they did was model Earth's atmosphere and then ran tests against the instruments on James Webb to see if the James Webb would be capable of detecting the gases that make up our atmosphere. And it passed with flying colors. So if we're looking for Earth-like, the James Webb has already been tested to be able to detect the major gases that are in our atmosphere. That's good news. And the Hubble is finding planet formation areas. This came out just the other day, of them finding this giant disk, a debris ring around a star that's almost 250 light years away, that's 150 billion miles across. So this is where planets are going to form. So the James Webb will do this much deeper. So we're able to find protoplanet structures now at great distances. That's pretty cool. Now let's go back. You talked about the Kepler and all their success, and they really proved how to do this. So this mission, which is still ongoing but truncated, was the first transiting space vehicle. Hugely successful. They just covered an area close to Cygnus, the Cygnus-Lyra boundary, which we see in the summer sky. And they monitored 145,000 stars over and over and over for several years. And then a partial failure in 2013, they had to cut it back, but they still found ways to make it useful. And now you have to listen to this carefully. Out of the information that they've teased out so far, and then some mathematical extrapolation, generate estimates that there could be as many as 40 billion rocky, Earth-sized exoplanets orbiting in the habitable zones of sun-like stars and red dwarfs within the Milky Way. As many as 40 billion Earth-sized exoplanets. Now, you say, well, that's a silly number, right? So let's assume that they're overestimating by a factor of 10, and it's only 10% of that. So, okay, there's 4 billion rocky Earth-sized exoplanets orbiting in the habitable zones of sun-like stars and red dwarfs. Doesn't change things much, does it? It's a huge, huge number, and they may be underestimating. We don't know. But the point is, they can pretty well prove from their little sample that it's very, very common. And, you know, I'm a believer. Now, the bigger guns are arriving. They're coming out. So, you all know a little about these. I'm sure all of you know some about all these, right? The Gaia, European Space Agency, we're going to talk about that. The James Webb Space Telescope, everybody's read about. And how many are you familiar with Tess, Cheops, W1st, and Sphere? If you know something about all four of those, raise your hand. I knew nothing about these. So this was the fun part of this exercise, because this is all real stuff. Tess is another transiting exoplanet survey satellite designed to search for Earth-sized exoplanets using the transit method. But they have different techniques, different technology, so it's a step forward. And it's going to do this for a couple of years, but they always last longer. So it'll monitor a couple 100,000 stars, and they expect to find thousands of planets and solar systems and Earth-like planets. So if this thing works, it's going to find a lot. And it arrived at the Kennedy Space Center 6 days after we were there to watch the launch of the Falcon Heavy. So this is getting ready, and it's going to launch sometime in the next 90 days. I never pay real close attention to the target date. Gaia has been up for a bit since 2013. It's a European survey telescope, and it's aimed at surveying a large part of the Milky Way. And their main focus is distance measurements, because our distance measurements techniques have been pretty shaky up till now, and it's important to get them right. But as bycatch in this, for stars within a distance of approximately 150 light years, Gaia is expected to find every Jupiter-sized planet with an orbital period of 1.5 to 9 years. Every is quite a claim. So they think they'll find 10,000 to 50,000 exoplanets. And that's in the not-too-distant future. So this is building. And when they find these, those are then targets for some of these other telescopes to go and work on. So it all just keeps feeding and building. Cheops, the characterizing exoplanets satellite, European Space Agency, for the study of the formation of known exoplanets. So, end of this year, perhaps, Precisely measure radius, mass, density of nearby transiting planets around bright stars, not around red stars. Targeting super-Earths near Neptune. So they're working in a different space, but trying to determine if they're rocky or gaseous. Said a different way, they're trying to find the biggest rocky planets, is the way I characterize it. And the goal is to identify candidates for follow-up atmospheric studies suitable for life. So you can't take the James Webb and have it go hunting. You have to find these things and tell the James Webb, go study that one, and here's when you do it. So that's how this all works. Then WFIRST, the Wide Field Infrared Survey Telescope, looking for potential life. Now we're aiming at potential life searches. Direct imaging of nearby planets, spectra of nearby gas giant planets, census of solar systems similar to ours, very small planets. Its actual main mission is to look for dark matter clues in the deep part of the universe, but it's also going to be used for this, and we'll do it as part of their studies. And then SPHERE, Spectral Polarimetric High Contrast Exoplanet Research Instrument. They're really stretching on these acronyms, aren't they? So this actually exists at the European Southern Observatory. It is a giant instrument on one of those 4 telescopes that make up the Very Large Telescope. And it has a very clever technological way to block out the star that they're pointing at, completely eliminate light from it, and therefore they can then start imaging the planets that go around it. And I tried to study the technology of this, and I don't understand a word of it, so I'm sparing you my attempt. So it's a ground telescope instrument. It's up and running. Detect and study new giant exoplanets by direct imaging. This is a breakthrough, to be able to do this from the ground. It became operational in 2014, and its first planet imaged successfully is 2017. They're still in test phases to get this going, but it's quite a deal. If you want to have some fun, go and look at the SPHERE instrument in the European Space Agency, which is a great website. This thing is amazing. Then there's Plato, the Planetary Transits and Oscillation of Stars, and it's going to launch in 8 years maybe. Find planets like Earth, both size and potential for habitability. It has different structure. It has 26 small telescopes and cameras in an array. So it's a very, very wide field survey camera. It's really ingenious, and my hat's off to them if they can pull this off. So they'll search for planets orbiting from up to 1 million stars, and precision measurements of radius, stellar age, planet mass. This is the first time you heard stellar age. Detect and characterize Earth-sized planets, etc. So this is 8 years from now. Things that are that far out, you don't get too excited about yet. So here's this camera array in it, and here's one of the telescopes and cameras. They actually have working prototypes of the telescopes and cameras. So, they're spending money on it. So, the punchline here. Trappist-1 was a stunning multinational Earth space instrument discovery. A pathfinder for collaboration and deep study of exoplanets. The story of collaboration in the Trappist discovery is heart-rendering to know that we can do that much collaboration. Many more instruments and tools are coming, ever-increasing capability. You all agree by now, I hope. The inventory of exoplanets and exosolar systems will soon be vast. Vast. So the more we find, the more we'll understand what planets are and what they can be, and unimaginable differences. So many questions are yet to be answered that we're working on. So students, pay attention to this. This is likely the most fascinating thing ever in the next 20 years. This is unprecedented in what's being learned. So you are going to live it, and it would be a tragedy for it to go on and you not be aware of it. You agree? Mm-hmm. Yes. So this is a message to students. This is your future. You are going to, if you pay attention, learn incredible things in this process. Thanks.
job, by the way. I have a simplistic question. How come there's no A designation?
Star.
It starts with B.
A the star.
A's the star.
Oh.
Trappist A,
Oh, okay.
I guess. I don't know. It started a
didn't
long
know
time ago. Yeah.
Thanks.
All questions. There's no such thing as stupid questions in this facility. There are inarticulate questions sometimes, but never stupid questions. Sometimes we have to tease out the real question. Nobody has a question.
Very thorough.
That's scary. You either all fell asleep or I covered it beautifully.
I thought you'd be asking questions.
Sorry, I decided to cut down on the questions today.
I hear family coaching. Anyway, I'll give Walker one question.
Yeah?
Yeah, one.
Yes? What's your question?
No, I'm allowing you one question.
Oh, sorry.
Since you're behaving so well, I thought I'd give you one question, but not two. Because once he starts, man.
Well, what year do you think people will start actually sending humans to the Trappist system?
I'm a pessimist on this, so my answer is never.
I would think sometime in the late next century.
My answer is
Really
never.
late next century.
But physics is on my side here. First of all, the first rockets that went up, we were able to get speeds when we sent some things, the Voyager, 40 to 43,000 miles an hour. You know how fast we can send them now? 40 to 43,000 miles an hour. And there's lots of notions of how to go much faster, but they're just that, notions. And those are notions mostly like capturing the sun's energy and things, and so we could move faster in the solar system, maybe to get to Mars.
Well,
But getting out of the solar system, solar energy is not going to get you very far. And so that's 39 plus light years away. Light travels at 671 million miles an hour, and we can go 40,000 miles an hour. That's a lot of zeros missing. And so a light year is 6 trillion miles. So 6 trillion times 40, we'll round it off to 40. That's 240 trillion miles. At today's velocity of 40, we'll even go to 50,000 miles an hour. It's forever. And the other thing is that you get going really fast, like trying to get close to the speed of light. If you get out there, you need to stop. And so it takes just as much energy to stop it as it does to accelerate it. So how are you going to stop it?
actually,
Gets harder. This is fun. That was it.
I didn't.
That was your question.
Sorry, I didn't mean by spaceship. I meant by wormhole.
Oh yeah, yeah.
I thought by the end of the.
There's
next
been
century
pretty
we'll
solid
perfect
proofs
wormhole.
about the mathematical theory of wormholes, which also includes the fact that they would collapse within trillionths of a second if you had one, because the energy it would take to keep it open is infinite. So that's wormholes for you.
So I guess
It's fun to read about.
we can say that we can start sending humans anytime, but
Right.
won't make it.
Right. In fact, we could probably collectively pick out somebody as a candidate. We won't go there tonight, though. But if you want to submit candidates, submit them to Monty. I jest. I think humor is helpful in learning.
Or you could freeze yourself and go.
Yeah.
If you
Yeah.
Or you could have populations that would multiply.
Yeah.
And maybe some human.
You got to feed them.
Oh,
It's a lot of food.
yeah, that's great.
Yeah. This details. All right. Well, this is a good audience. I hope this is interesting to you. I choose these because I don't know anything about them, and then find oh my God, all these acronyms of these things in the future. I didn't know about any of them, and they're real. You judge real by how much money is being spent. That's the only litmus test. If they're spending a lot of money and putting their reputations on the line, it's real. And these are all real. Elaine, you look like you're formulating a question. Are you ashamed?
I'm sighing.
Oh, all right. We don't have a third group out there, do we? Good. I'm out of gas. Thank you.
Nice job.
They enjoy it.